Now that we've learned about radian measure in this section, we're going to do some applications. We're only going to do two. And the first is arc length. All right, so let's derive a formula for the arc length of the length of an arc intercepted by a central angle. So let's draw a circle here. Let's assume the circle is of radius r. Here, let me just draw something more generic. All right, so let me just draw a central angle here. Okay, so I'm going to say the radius is r, and I'm going to call the central angle theta. Now, one of the assumptions here, I'm assuming theta is in radian measure. Okay, so as I derive the formula, I'm going to assume theta's in radians. And we're going to call the arc length, so the length of the arc intercepted by the central angle, we're calling S. Okay, so we want to develop a formula. Now, does it seem reasonable that if I took the measure of angle theta divided by the measure of the angle all the way around, that would equal the arc length here, S, divided by the arc length all the way around? Let me say that one more time. So I'm going to create a proportion here. So this angle, theta, divided by the angle all the way around, is this arc length divided by the arc length all the way around. That is true. Those two proportions are equal. So let's set this up. So the central angle theta in radians divided by the angle all the way around. Now I'm sticking to radians for theta, so the angle all the way around is in radians too. That's 2 pi. Notice I didn't put units because radians over radians would cancel anyway. And I claim that would equal to this arc length here, S, say feet, inches, miles, whatever it is, divided by the length of the arc all the way around. Well, what's the length of the arc all the way around? That's the circumference of a circle, which is 2 pi r. And again, if that were feet over feet, the units cancel. So this is just a number equal to another number. Okay, well, let's do some simplifying here. If I cross multiply, I get 2 pi r theta is 2 pi s. Right, if you cross multiply. And notice both sides have a 2 pi, so if you divide by both sides by 2 pi, you get S is r theta. Nice formula here. S is r theta. Actually, I mean, you kind of saw this coming when I was developing the formula that pi radians was 180 degrees. Wasn't the arc length? Remember, I said, like, you know, an angle of 1 radian cuts out an arc of 1 times r. And if you had 2 radians, it cut out 2r. I mean, we saw that before. Okay, so S is r theta. Now, what's the key important thing here? Theta, I developed the formula for theta in radians. If you plug in theta into this formula, theta has to be in radian measure when you plug in. If this formula spits out a theta, in other words, you plug in an S and an R and you find theta, theta's in radians. So plugging in, theta must be in radians. Spitting out, theta will be in radians. All right, let's do an example. Now, this picture is in the book. It's a figure in the book. So they give this pulley. So they have a pulley here. And in the picture, they give you the radius is 9.27 inches. And then they have this weight hanging down. Okay, so in the wording of the problem, they don't tell you the radius, but the radius is given in the figure. It's 9.27 inches. The problem says, how many inches will the weight in the figure rise if the pulley is rotated through an angle of 71 degrees 50 minutes? 71 degrees 50 minutes. Okay, so this rope is attached to a weight and to the pulley. And we imagine this, you know, there's a handle and we're rotating this thing up through an angle of 71 degrees 50 minutes. So the angle here is 71 degrees 50 minutes. And so how high will the pulley, how high will the weight rise? Okay, now what's the assumption here? When you turn the handle on this pulley, this rope is attached right here. So where's the rope going to go? Right? When you turn the pulley, the rope is going to start wrapping around the wheel here. Okay? So the amount that the weight, in inches, right, the length that the weight comes up is going to be the same amount that wraps around the pulley here, the amount of rope that wraps around. So notice nowhere in the problem does this say find the arc length, but this is an arc length problem. It's a nice problem because you have to understand what's going on to know that it's an arc length problem. Well, we have the formula, right? S is R theta. We're looking for this S, right? R is given and theta is given. So we're just looking for S. Now, do we just say 9.27 times 71 degrees 50 minutes? No. I mean, even if we change this to decimal degrees, what's the kicker here? To use the formula, to plug in for theta, theta has to be in radians. So we have to do some conversion on the 71 degrees 50 minutes to start with. So 71 degrees 50 minutes. First, what you want to do is change that to decimal degrees. Remember, when we go from degrees to radians and radians to degrees, we never involve minutes. So first we want this decimal in decimal degrees. So that's 71 plus 50 over 60, which is about 71.8. I'm going to use a lot of decimals here. It's a bunch of threes, right? Okay. And now I want to convert this to radians. So 71.833333. Well, I only did 4. Fine. Degrees over 1 times. So degrees I want in the bottom and radians I want in the top. So the degrees will cancel, I'll be in radians. And remember, pi radians is 182 degrees. Now I'm going to go ahead when I type this, I'm going to type the pi in and get a decimal. I don't want the exact value here like when we did conversions. I've already rounded here, so I can't get exact anyway. 71.83333 times pi divided by 180. Again, you should punch along with me. And I'm getting about 1.2537 radians. So that's what theta is in radians. Now doesn't this answer make sense? Always see if your answers make sense. Remember, 1 radian was about 57 degrees, so this is 1 and change. Okay, now let's go to our problem. S is our theta. S is what we're looking for. R was 9.27. And theta is 1.2537. Don't put the units here. When you put radians and inches, you're going to get confused. Don't worry about the units. And then we just multiply those together. 9.27 times answer. If I go to a couple places, it's 11.62. Now, what are the units on this answer? Think about what type of thing S is. S is a length. The answer is not radians here, right? It's length, so it's the same units as the radius, inches. And does this answer make sense, right? Think about it. If you rotate through an angle of 1 radian, the arc length and the radius are the same. So if this were 1 radian, it'd be 9.27 and 9.27. 70, I already mentioned, 71 degrees 50 minutes is a little more than a radian. Right, 1.2, so the answer should have been bigger than 9.27, which it is. Okay, so that one's not too bad. Once you realize what's going on, and now the part B of this problem says, through what angle to the nearest minute must the pulley be rotated to raise the weight 6 inches? Let me draw the picture again. It's 9.27 inches. And this one says through what angle. So now we're going to rotate through an angle we don't know. I'm just going to draw something. Theta. I have no idea if the answer is acute here. I just drew something. Through what angle to the nearest minute must the angle be pulley be rotated to raise weight 6 inches? So for the weight to go up 6 inches, that means you have to rotate. You have to wrap around 6 inches of rope, which means the arc length is 6 inches. Okay, well, S is r theta. So here, S, the arc length is 6, the radius is 9.27, and theta we don't know. Okay, so divide both sides by 9.27, theta is 6 over 9.27. If you want to get some decimals, you can. 6 over 9.27 is about 0.64725. What are the units on this answer, theta? Now, it doesn't matter what the problem asks for. I told you before when we derived the formula, if you plug in for theta, theta must be in radians. If the formula spits out a theta, theta's in radians. This is an angle in radian measure, not it has nothing to do with what the problem asks for, what the problem gives you, right? This gave you degrees and minutes, but that doesn't mean that's what you plug in, right? We had to convert. So theta is 0.64725 radians. Now the question is that what the problem asked for? No. The problem said through what angle to the nearest minute. So we need to convert these radians to degrees and minutes. Okay? So theta is 0.64725 radians. So to get rid of the radians, I put the units in the denominator, and I want to go to degrees. Notice in this problem, we had degrees and minutes, we went to decimal degrees, then we went to radians. Here we're going to go radians to decimal degrees to degrees and minutes. And 180 degrees is pi radians. Again, when I punch this in, I'm going to include the pi as well. So that 0.647 times 180, times 180 divided by pi. Okay, so this is about 37.0846 degrees. That's decimal degrees. And we've talked about how to change to degrees, minutes, seconds, so I assume you can do that either on the calculator or just on your own. So I'm getting 37 degrees. It's 5 minutes and 4.7 seconds. So you'd only round up if you had at least 30 seconds, which I don't, so this is 5 minutes. Okay. And this answer makes sense. Notice, right, if theta were 1 radian, the arc length would be the same as a radius, 9.27. This is less than the radius, so the answer is going to be less than 1 radian, which it is. Right, it's not even close. Okay, so that's that problem. Okay, so the next problem is a geography problem. Okay, so I'm going to try to draw an embarrassing map of the United States. And just write that, or you don't need to draw it if you don't want to, but put it way over to the side because it really isn't going to have anything to do with where we're headed. So, or maybe up at the top of your notes. Okay, I'm going to try to draw the United States. This is so terrible. I don't even know what I'm doing. Okay, Louisiana doesn't really exist here. Okay, that's not too terrible, I suppose. Okay, that's the United States. It says Charleston, South Carolina, and Toronto, Canada are 1,100 kilometers apart and lie on the same north-south line. Okay, so South Carolina, at least I know South Carolina's over here. I'm just gonna, I don't know if Charleston's on the coast or not, so okay, there's Charleston. That's, yeah. Okay, there's Charleston. That's probably more Georgia than South Carolina. And Toronto, Canada are 1,100 kilometers apart on the same north-south line. Okay, so presumably Toronto is up here, Toronto's in Canada, and they're on the same north-south line. So this is Charleston, South Carolina, and this is Toronto. They're on the same north-south line, and they're 1,100 kilometers apart. Okay, so that's the first sentence. The latitude of Charleston is 33 degrees north. So the line of latitude, remember longitude's vertical, latitude's horizontal. So imagine this on a globe. This is at 33 degrees north, being north of the equator. Okay, so again, we're going to change the picture here to actually get it to what we want it to look like, but I want you to understand what the context here. Okay, so Toronto's up here, Charleston, South Carolina is here. They're 1,100 kilometers apart on the same north-south line, and Charleston's at 33 degrees north. The question is, what's the latitude of Toronto? So we have another line of latitude up here, and we want to know what is that? Now, it's certainly more than 33 degrees. Remember, the equator is at 0 degrees. So it's more than 33 degrees north. Okay, so imagine this is on a globe. Okay? Now, think about, so this isn't the picture we want to help us solve the problem, but this helps me visualize what's going on. Right? Spin the globe. So where this line, think about if this were on a globe and you were looking at it and you started spinning it, what would happen to this line? The line would start moving as you spin it, right? So spin it until this line segment reaches the very, very edge. So you could just see it. And if you spun a little bit more, it'd go back behind, you wouldn't see it anymore, okay? So imagine that. So you spin the globe, so where this line, you've marked it on the globe, spin the globe, this line starts moving until it gets right on the edge so you can just see it. And if you spin it anymore, it'll disappear, you won't see it. And then right where that line is on the edge, right? Your globe will be sticking out at you like this, and this line would be over here. Imagine slicing the globe in half. So that's right on the edge, and you slice it in half. So that's what I'm going to try to draw here. So this is the globe, and I've sliced it in half, right? The equator's here. So here, the equator's on my original picture, the equator's down here. So if I rotate, where's that line going to be? It's going to be up here, right? So this line segment is going to be here, right on the very edge, and I've sliced the globe in half. There's the center. Okay, so the equator, you know, is here and here. Right, I've sliced the globe in half. And what is this 33 degrees north? Right, so here's Charleston, South Carolina. 33 degrees north is the angle that's measured from the equator going up. So from here to here, this angle right here is 33 degrees. That's the angle right here. This is not the scale. Right? Notice 33 degrees south would be the point right here, right? Where, okay? Okay, so what are we looking for? We're looking for the latitude of Toronto, which is the angle from the equator up to here. Well, we already know from here there's 33 degrees, so if we could just find this theta, we could add them together, right? So we don't need to measure from here, we just need the theta here. And the distance between the two cities was 1,100 kilometers. Notice I've changed this by redrawing this picture the way I've done it. This becomes an arc length problem. And again, nowhere in the problem does it say find the arc length. You have to understand this is an arc length problem. Now, what else do we need to know to finish the problem? We need to remember S is r theta. We need the radius of the Earth. Now, they don't mention it in this problem. It's actually in example 2 in the text. And they give you the radius of the Earth as 6,400 kilometers. I would give you that. You wouldn't have to memorize that. Okay, so the radius of the Earth is 6,400 kilometers. Again, I would tell you that on a test or quiz. Okay, okay, well, we know S, we know R, and we need theta. We know the formula. S is r theta. The arc length, they told us, was 1,100 kilometers. The radius of the Earth is 6,400 kilometers, and we're looking for theta. So the hard part here is figuring out what is the information giving. Once you understand how this is, the math is easy. So theta is 1,100 over 6,400. Now again, what are the units on this theta? We use the S equals r theta formula. It's spitting out a theta. This is in radians. Okay? And you could do latitude and longitude in radians, but typically we do degrees, and they gave us in degrees, so we want to be consistent. So we need to find this theta in degrees. I'm just going to go ahead, instead of getting a decimal, I'm just going to go ahead and do the conversion right here. Radians in the denominator, degrees in the numerator. And how many degrees is how many radians? Pi radians is 180 degrees. So if we punch that in, again, punch along with me, I got about 9.85 degrees if you round to 2 places. It's 9.8477. Okay, now don't get so excited we got theta that you stop with it. We have to answer the question. The latitude of Toronto is, right, that's the theta is 9.85. That's just from here to here. We have to measure from the equator, so it's 33 degrees plus 9.85 degrees, which is 42.85 degrees north, right? North meaning we're above the equator. Okay, that wasn't too bad. So the actual math on that problem is not that bad once you understand the situation. So the distance between the cities is the arc length. Okay, so that's interesting. It's a nice application of trigonometry here. Okay, so that was one application. The other application is sector area. So let me derive a formula for sector area just like we did with the arc length. So imagine we have a circle and we have a central angle just like before. Let's assume the radius is r and the central angle is theta, just like we did before. But instead of focusing on the arc length, the length of the arc intercepted by the central angle, let's look at the sector area. So the area of the pie piece here I'm calling A. So the theta is the angle here, and the A is the area of the sector. Okay, so the little pie piece there is called a sector. Okay, so I'm going to derive it the exact same way we did the arc length. So theta is in radians again. Okay, so if you plug into the formula for theta, thetas in radians, if the formula spits out a theta, thetas in radians. Okay, so I'm going to use the same procedure I did before. If I took the angle theta divided by the angle all the way around, both in radians, that fraction is equal to the area of the sector here divided by the area all the way around. Let me say that one more time. So if I took the fraction, that angle theta, the central angle, divided by the angle all the way around, that would equal the same as the fraction area of the sector divided by the area all the way around. Those in fact are equal. So what did we get? So theta, the measure of the angle in radians, divided by the measure of the angle all the way around, that's 2 pi. So that part's just like it was for the arc length. That's equal to the area of the sector, which we're calling A, divided by the area all the way around. Well, the area all the way around is the area of the circle, and the area of a circle is pi r squared. Okay, so if I cross multiply again, I get pi theta r squared is pi times 2a. I put the pi's out front just so you can see they both have a pi. So the pi's cancel. Right, so pi r squared is 2a. And if you multiply both sides by a half to get rid of the 2, that's what you get. So the area of the sector is 1/2 theta r squared. So to find an arc length or a sector area, all you need is theta and r. But again, theta is measured in radians. So if you plug in for theta in this formula, theta has to be in radians. If the formula spits out a theta, theta is in radians. Okay, so that's our formula for the area of the sector of a circle. And we have an example here. Find the measure in radians of a central angle. Okay, well, let me go ahead and draw a picture here. So there's a central angle. Remember, central angle is an angle whose vertex is at the center of a circle. Find the measure of a central angle, so I'll call that theta, of a sector of area 16 square inches, so the area is 16 square inches, in a circle of radius 3 inches. Okay, pictures help you visualize what's going on. Okay, find the measure in radians of a central angle. So we're looking for theta. Now, please don't, the units are square inches. Don't square the 16. The 16 is not being squared. It's the units that are being squared here. Right? 16 inches is a length. 16 square inches is a length times a width, right? Okay. Well, the formula says A is 1/2 theta r squared. That's our formula for the area of a sector of a circle. Let's plug in what we know. So 16 is A. Again, don't square the 16. A is 16. The area is 16. 1/2. Theta I don't know. Now the radius is 3, so you have to square the 3 to get, 3 is 9, right? All right, let's do some simplifying. So 16, that's 9 over 2, that's 9/2 theta. And you could divide both sides by 9/2. That's the same as multiplying by 2/9, right? So if I multiply by 2/9, I'll get a 1 here. So theta is 2/9 of 16, which is 32/9. I'm just going to leave it as a fraction, right? There's no pi or anything, so I'll just leave it as a fraction. Right, now do we need to do anything? What are the units on this answer here? Well, we use the area formula and it spit out a theta. This is in radians. So what do we need to convert to here? Okay. What did the problem ask for? The problem said, find the measure in radians of a central angle. There's nothing to do here. We're done. Right? Please read the instructions and follow the instructions. The only reason in the previous example, we had to convert the first example with the arc length, they gave us an angle in degrees and minutes. You had to change to plug into the formula. And the second problem, where we were looking for theta, the problem specifically said to the nearest minute, so we had to convert. This one just says find theta in radians, so it spit out theta in radians, so we don't have to convert. Don't waste your time doing work you don't need. Okay, so that's our section on applications of radian measurement.